Hello everyone, so welcome back for the third time this week where we are talking about the gas turbine cycles. So over previous two lectures we have learned about the ideal cycle for the gas turbine, which is the Brayton cycle. We have discussed about different aspects of the Brayton cycle, particularly the role of the pressure ratio in determining the thermal efficiency and the work output or net work output from the Brayton cycle. And then in the second lecture we have discussed two very common methods of enhancing the performance of a Brayton cycle based gas turbine, which are the use of intercooler with multistage compression, or I should say use of multistage compression with intercooling in between, and the use of multistage expansion in the turbine with reheating in between. So, just to have a quick recap of that, these are the two schemes that we have discussed. In one of them, the compression stage is divided into two stage or maybe more than two stage. The first one is called the, here in the diagram we have just two stages of compression. The first one is a low pressure compressor, second one is a high pressure compressor. So, the air which is coming out of the low pressure compressor, that is supplied or that is allowed to pass through an intercooler where its temperature is reduced ideally back to the initial temperature, then it goes to the second stage of compression to reach the desired pressure at this point number 4. We have also discussed in detail about the optimum value of the corresponding pressure ratio, and we have seen that pressure ratio for each of the compression stage should be equal to each other in order to have the minimum possible work requirement for the compressor. That is, in this case we should have P2 upon P1 to be equal to P3 P4 upon P3, and if you are talking about more stage number of stages, then the same way every stage should have the same pressure ratio in order to have the maximum effect of this intercooling. And similarly, if we can separate out the expansion in multiple turbines, then we can have two stages of turbine as shown in diagram. Here we have an HP turbine or high pressure turbine. So, the combustion products that are coming from the combustion chamber are allowed to pass through the high pressure turbine, where they are expanded to some intermediate pressure level. Then the gas or exhaust coming out of the high pressure turbine is subjected to a stage of reheating in the second combustion chamber, where ideally it is heated back to its initial temperature, and then it goes to the second stage of expansion to reach the final pressure level P6. So, like in case of intercooling, for ideal scenario, for ideal intercooling we should have T3 to be equal to T1. Similarly, in case of reheating, in order to have the maximum possible effect, that is maximum possible gain in the work output, we should have T2 we should have T3 to be equal to T5. That is, the temperature with which the gas is entering every stages of expansion should be equal to each other, and also to have the maximum possible work output from the multi-stage expansion, we should have equal pressure ratios in all the stages. Like in this case, if we look in for the HP turbine stage, the pressure ratio is P3 upon P4, and for the LP turbine stage the pressure ratio is P5 upon P6. So, to have maximum effect, these two should be equal to each other. The second one, this one of course we have not derived, but that is a direct consequence of this. I would request you to try to derive the same relation assuming T3 equal to T5. But now, what are the effects of intercooling and reheating? For intercooling, of course, we are getting a reduction in the compression work, while the turbine work may remain the same if there is no reheating or no change in the turbine side. Therefore, there is an increase in the net work output and an improvement in the work ratio or a reduction in the back work ratio. However, because of the presence of intercooling, there is an increase in the energy output requirement, because had there been no intercooling, whatever would have been the temperature of the gas at the end of compression, because of the presence of intercooling the temperature is much lower, and therefore, to heat the gas back to the desired temperature T5, we need to spend a larger amount of energy, which despite the reduction in the compression work requirement generally leads to a reduction in the overall thermal efficiency. So, because of the effect of intercooling is a reduction in the compression work, while the turbine work remains the same, and therefore, the net work requirement that increases, because net work requirement is turbine work minus compressor work. However, the heat input requirement that also increases, and the combined effect of these two generally is a reduction in the thermal efficiency. and also the bulk of the system increases because we are going for multiple stages of compression plus one additional heat exchanger in the form of intercooler in between. So, we need more space to house the same thing and also more complicated piping arrangement. What about the reheating then? For reheating, again we are having an increase in the turbine work. So, in this case the turbine work is increasing and the compression work may remain the same if there is no change in the compression side. So, the effect will be the net work output, which is the turbine work minus the compression work, that is going to increase. However, here we are having additional energy requirement because here we have to supply energy into combustion chambers. We are adding energy in this combustion chamber 1 and we are also adding energy in the combustion chamber 2 because of the reheating requirement. Quite often we call this one to be Q primary, because even if there is no reheating, this is the amount of energy you always have to supply, whereas this is called the Q reheat, which is the additional energy burden that is coming because of the presence of this reheater. So, the total energy requirement, which is the combination of this primary energy requirement or primary heat requirement and the reheat side heat requirement, that is having an increase leading to a reduction in the thermal efficiency as well. So, we are having increased turbine work output and therefore increased net work output, and here similar to the intercooling, a better work ratio or a reduction in the back work ratio, but there is increased energy input requirement leading to an increase or rather reduction in the thermal efficiency. And another big implication of this reheating is that the exhaust temperature, this T6, is much higher. If there is no reheating present, then what would have been the exhaust temperature? This exhaust temperature with the presence of reheater is significantly higher. There may be 300-400 Kelvin order of temperature difference, which is one big issue to be resolved with reheating. So, this higher exhaust temperature is something that we have to be careful about with the use of reheating, and of course, we have additional space requirement because of additional combustion chamber and additional stages of turbine and more complicated piping arrangement. But compared to the intercooling, reheating generally requires less space because we may use the same combustion chamber, that is CC1 and CC2 may be the same temperature, only additional pipings will be required for this, whereas in case of intercooling we need a separate heat exchanger. Now, we can see that while the multi-stage compression with intercooling and multi-stage expansion with reheating both are leading to increase in the net work output and improved work ratio, but both of them are causing a reduction in the thermal efficiency. So, we also have to devise some option which gives us both things, that is the additional work output that we are getting, that must be retained, but also the energy requirement, energy input requirement, that needs to reduce so that we can have an increase in the thermal efficiency as well, and that option is regeneration. Regeneration employs another heat exchanger which is called the regenerator. The idea is that the energy of the exhaust gas coming out of the turbine will be utilized to preheat the air before it is allowed to go to the combustion chamber. Like we have seen, with the use of reheater, the exhaust gas temperature can be very high. Even when there is no reheater, the exhaust gas temperature will be quite significantly higher compared to the air temperature coming out of the compressor. So, if we can devise a heat exchanger just like whatever is shown in this situation, the exhaust coming out of the turbine is allowed to pass through the heat exchanger, where it is rejecting its additional heat or excess heat to the compressed air coming out of the compressor. Thereby, we are having an increase in the air temperature because this air temperature T3 will be greater than T2, and so it is entering the combustion chamber at a higher temperature. So, the total energy requirement in the combustion chamber will be lower because ultimately we want to gain the same temperature T4. If there is no heat exchanger, no regenerator, then the temperature rise that the air or the gas must experience in the combustion chamber should be equal to T4 minus T2, but because of the presence of this regenerator, the temperature change that we want to have is T4 minus T3, and T3 can be significantly higher than T2, causing a significant change in this energy requirement or the temperature rise requirement T4 minus T3, because that can be significantly lower than this T4 minus T2. So, total energy requirement for the combustion chamber, energy requirement in the combustion chamber, that reduces, whereas it does not have any effect on the work output, because the work output depends on the turbine work output and the compression work input requirement. So, your compression work remains the same, the turbine work also remains the same. So, the net work output, which is the turbine work minus compression work, that also remains the same, but the heat input requirement Q in, that is reducing, because some part of the heat is being recovered from the exhaust gas. Therefore, the thermal efficiency, which can be written as the net work output by heat input, that is having a rise in this. So, regeneration is an option of increasing the thermal efficiency without affecting the work output from the system, because its effect is not to change the work output, rather to increase the heat input requirement. The simple diagram is shown, just be careful here, we are not at all talking about any intercooling or reheating, we are just talking about the regeneration as an option. So, one is the point at which air is entering the compressor, and had there been ideal compression, that is isentropic compression, it should have reached 2s, but because of the presence of irreversibilities in the compressor, it is reaching the point 2. Then 4 is the temperature, let us say T4 is this temperature, which is our desirable temperature at the inlet to the turbine. Now, if we want to have this entire temperature rise being done in the combustion chamber, then T4 minus T2 amount, or amount of energy that you have to supply to the air, that will be equal to the mass of air into Cp air into T4 minus T2. But here we are having the regeneration done, because of which this T2 to T3, or rather I should say T2 to T3, this amount of temperature rise has taken place. So, the amount of energy increase that has to be taken place in the combustion chamber is now the same Ma into Cpa into not T4 minus T2, rather it is T4 minus T3. And from where this energy is coming, as shown in the diagram, the same thing we can get from the TS diagram as well. So, 4 to 5 is the expansion in the turbine. Had there been isentropic expansion, we should have reached 5s, but here we are reaching this T5. Now, instead of allowing this gas to go out as its own on its own, we are using the energy from the gas, so that the gas temperature in the regenerator reduces from T5 to T6, and then only it is allowed to go out to the surrounding. So, in the regenerator, then we are actually making use of the waste heat of the exhaust gas, thereby it is always a very profitable option. We generally go for a counter flow kind of heat exchanger, so that the air as it moves through, like if we think about a counter flow heat exchanger arrangement, okay, let me show from this diagram only. A counter flow heat exchanger arrangement is shown. So, as the air is flowing in this direction and the gas is flowing in this direction, air is always encountering a gas at higher temperature, because at the inlet the gas temperature is low. Similarly, at the exit the heat at the inlet air temperature is low, similarly at the exit the gas temperature is also low, and they are in close proximity of each other. So, gas temperature being higher, it is still able to add energy to the air stream, whereas towards the exit side where the air temperature is high, the gas temperature is also the highest. So, this counter flow heat exchanger arrangement gives us quite high effectiveness, and therefore, we can recover significant amount of energy from the exhaust gas. If we are talking about an ideal regenerator, then ideally you would like to have the air temperature at the end of regeneration, this T3 to be equal to T5. That is, this is the ideal scenario. In ideal scenario, you want the air temperature at the end of regeneration to be equal to the gas temperature at the beginning of regeneration, and similarly the gas temperature at the end of regeneration, that is T6, that should be equal to the air temperature at the beginning of the regeneration process or the exit of the compressor, that is equal to T2. This is the ideal scenario, but practically we may not be able to get this, because there may be heat losses present in the system, and also we need to have a certain amount of temperature difference between the air and gas, so that we can facilitate the heat transfer. Therefore, practically this T3, if we talk about the practical sense, practically your T3 will always be less than T5 and T2 will always be less than T6. If we neglect any kind of heat loss from the system, then the total amount of energy rejected by the gas can be represented as mass flow rate of the gas into Cp for the gas into the temperature change of the gas, which can be written as T5 minus T6. Here of course, we are using the average specific heat, and this should be equal to the energy gained by the air, which is mass flow rate of air into Cp for air or average Cp for air into its temperature rise, which is T3 minus T2. As we are talking about a heat exchanger, we generally prefer to define one effectiveness to characterize the or to compare the actual performance with the ideal performance. If we look at the diagram for an ideal scenario, here look at what we have. Here 2 is the point at the end of compression and 5 is the point for the gas at the end of expansion. So, while in the ideal regenerator, air temperature at the end of regeneration should be equal to T5, but practically it remains as T3, which is lower than T5. T3 remains lower than T5. Similarly, the gas temperature at the end of regeneration, that is 6, is not able to reach up to 2. So, we have T2 less than T6 again. We generally prefer defining an effectiveness, as I have just mentioned. Effectiveness for a regenerator is similar to the way we define effectiveness for any heat exchanger. Let us say epsilon. It is given as the actual heat transfer by maximum possible heat transfer that can take place, or actual rate of heat transfer divided by maximum rate of heat transfer. Now, if we think from the air point of view, then what is the actual energy gained by the air? Then we can write that to be equal to actual enthalpy change of the air, that is H3 minus H2. But had been we are talking about an ideal process, then it should be equal to H5 minus H2, or I should say H5 prime, where 5 prime refers to this particular point, where the air temperature becomes equal to the gas temperature at the beginning of regeneration, that is T5 is equal to T5 prime. So, H3 minus H2 upon H5 prime minus H2, H5 prime minus H2 is the maximum possible energy gain that the air can have. Now, if we neglect any heat loss and changes in kinetic energy and potential energy, then this is the way we can represent this. And if we now assume the specific heat for the air to be constant, then we can write mass flow rate of air into Cp of air for this condition, average Cp for between this temperature T2 and T3 into T3 minus T2 divided by mass flow rate of air into Cp for air. I am putting a double bar here. This double bar refers to the average value of specific heat for air between the point T5 and T2. So, it should be equal to T5 minus T2, which gives us, if we use the cold air standard assumption, that is all the specific heats and properties are assumed to correspond to the atmospheric temperature, then Cp and Cp bar and Cp a double bar, they are equal to each other. So, we get if effectiveness to be equal to T3 minus T2 by T5 minus T2. As it is becoming a ratio of temperature differences only, this is often called the thermal ratio. So, in case of gas turbine, to characterize the regeneration process, we use effectiveness or thermal ratio, either of the names can be used. Now, before we move any further to perform any mathematical analysis of this gas turbine cycle with regeneration, we have to look into the practical sense. We can go for a regeneration process when, can you say when? When we can go for regeneration process? What is the idea of regeneration? The idea of regeneration is to make use of the heat contained by the exhaust gas to preheat the air before entering the combustion chamber. Now, in order to have the heat being heat transfer from gas to the air, the gas temperature has to be higher than the air temperature, and that is, I should say, the gas temperature at the end of expansion has to be higher than the air temperature at the end of compression, that is T5 has to be greater than T2, and then only it is possible to design a regenerator. If we have a scenario something like this, where the temperature at the end of the expansion process, that is T4, that is less than the temperature of air at the end of compression process, like in this case T2 is greater than T3, sorry, T2 is greater than T4, and so regeneration is not possible in this case. Even when T4 is greater than T2, unless it is a significantly large temperature difference, we should not go for a regenerator, because the incorporation of the regenerator there gets into picture several things, like we have additional capital cost requirement, we have maintenance requirement for the heat exchanger, and also large surface area requirement if we are talking about a very small temperature change between T4 and T2. So, the heat exchanger or regenerator can be included in the design only when the gas exit temperature is significantly larger than the air temperature at the end of compression. Now, total amount of heat input requirement Q dot in with the heat exchanger, how much will be that? Total heat input requirement in the combustion chamber, that will be equal to m dot air into Cp air or average Cp of air into T4 minus T3, whereas the amount of heat input requirement without heat exchanger, how much will be that? That will be equal to m dot air into average Cp of air into T4 minus T2. T3 being significantly greater than T2, we can definitely have this term to be greater than the other term, and therefore, the effect of regeneration is to cause a reduction in the total energy requirement in the combustion chamber, and accordingly we have an increase in the thermal efficiency. So, this is how a practical regenerator works, where we have 1 to 2 here. Of course, we are not considering the irreversibilities inside the turbine and compressor, that is we are taking isentropic efficiencies of both compressor and turbine to be equal to 1. Then 1 to 2 is the compression process, 2 to 5 is the regeneration process, regeneration for air heating, then 5 to 3 refers to the combustion process. So, the Q regeneration, as we have seen, will be equal to mass of air into Cp of air into T5 minus T2, and Q in, that is the amount of heat that we required in the combustion chamber, will be equal to mass of air into its specific heat into T3 minus T5. If we are talking about an ideal regeneration, then the temperature of air at the end of regeneration process should have been 5 prime, which is equal to T4, that is gas temperature at the end of expansion. However, because of the practical issues, T5 we are never able to reach this temperature of 5 prime. Generally, we are restricted to point number 5. Similarly, the gas temperature has dropped to T6, ideally should have dropped to this particular point, but again because of the practical issues we may not be able to lower the gas temperature up to the level of T2, it is restricted to T6. And this amount of energy, which is the mass of gas into Cp for gas into T4 minus T6, this is the amount of energy we are saving because of the regeneration, otherwise it would have been lost to the surrounding. Now, if I talk about from the thermal efficiency point of view, we already know that the thermal efficiency for a standard Brayton cycle without any reheat, regeneration etc. is given as 1 minus 1 upon Rp to the power k minus 1 upon k. However, when regeneration is there, we also have to consider the maximum and minimum temperature of the cycle. Now, the cycle shown here, the minimum temperature is T1, maximum temperature is T3. It can be shown that I am not doing the derivation, the thermal efficiency with regeneration, that will be coming to be 1 minus T1 upon T3 into Rp to the power k minus 1 by k. So, it depends on the pressure ratio and also it depends on the temperature ratio, maximum to minimum temperature of the cycle or minimum to maximum temperature of the cycle. As you can see, the ratio of minimum to maximum temperature that keeps on increasing, the efficiency also keeps on reducing. As the number of stages of compression and expansion that keeps on increasing, then we have scenario something like this. Look at, so how many stages of compression you can see here. There are so many stages and each of them are having as the identical pressure ratio and a perfect intercooling in between. Similarly, on the turbine side we are having multiple reheaters, each of them having the same pressure ratio, and accordingly we are having ideal reheat for this. In that case, how this curve is looking like, or this total cycle that have been plotted, definitely this cycle is looking quite similar to the Ericsson cycle, is not it? Because in case of Ericsson cycle also we had two constant temperature process and two constant pressure processes, exactly what the Brayton cycle reduces to when it has infinite number of compression stage and expansion stage. However, practically speaking, we never go for more than 2 or 3 stages of compression and expansion. 2 or at most 3 are sufficient. But if theoretically we can visualize infinite number of stages, then the Brayton cycle will reduce to the Ericsson cycle, where of course the Brayton cycle needs to have all its improvement, that is reheat, regeneration and also intercooling. So, this is how a practical gas turbine cycle will look like, where we can see there are 2 stages of compression, compressor 1 and compressors 2, in between we have an intercooler. We want ideal intercooling, for which we have T3 equal to T1 and we have the pressure ratios to be equal for both stages, that is P2 upon P1, pressure ratio for stage 1 should be equal to P4 minus P3. And also in case of ideal scenario, there is another factor that we neglect, which is no pressure drop. As the air is allowed to pass through the 2 stages of compression and also the intercooler, there may be some loss in the pressure of air, but we are neglecting any kind of pressure drop and we are considering ideal intercooling. Now, the air which is coming out of the compressor with temperature T4, that goes to the regenerator, where it gains energy from the exhaust gas and enters the combustion chamber with temperature T5. The exhaust from the combustion chamber first goes to the turbine number 1 and the exit from turbine 1 is supplied through the reheater, where it is energized again, and again is quite similar to the intercooler. In ideal scenario, we want T8 to be equal to T6 and we want the pressure ratios to be equal to each other. Now, exhaust from the second turbine T9, that goes through the regenerator, thereby increasing the thermal efficiency of the cycle. We shall now be doing couple of numerical examples just to see the numerical effect of regeneration. The first problem, this is actually a repetition of one problem that we have solved in the previous lecture. Just read the problem statement carefully. We are talking about an ideal gas turbine cycle with overall pressure ratio of 8. It is operating with 2 stages of compression with intercooling and 2 stages of expansion with reheating. Air enters each compression stage or each compressor stage at 300 Kelvin and each turbine stage at 1300 Kelvin. We have to determine the back work ratio and thermal efficiency. We have solved this problem in the previous lecture, but now we have a change. Here we have to consider an ideal regenerator with 100% effectiveness. The value of K is given, we may consider the value of specific heat also. So, the same problem we have solved in the previous lecture, but without regeneration. Now, this is the scenario where 1 to 2 and 3 to 4 are the 2 stages of compression, 6 to 7 and 8 to 9 are the 2 stages of expansion, 2 to 3 refers to the intercooling process, similarly 7 to 8 refers to the reheating process. So, how to approach this particular problem now? We have solved this problem in the previous lecture, but without the regeneration. So, the similar procedure are going to follow here also. Here overall pressure ratio is given as 8. Overall pressure ratio refers to what? It refers to the pressure at the end of compression, which is P4, and pressure at the beginning of compression, which is P1, that is equal to 8. And here we are talking about an ideal cycle, that is as no information is given. So, we can assume the compression the multi-stage compression process to be an ideal one, that is with perfect intercooling. If it is having a perfect intercooling, then we have the pressure ratios to be equal, that is P2 by P1 should be equal to P4 by P3, and as we are neglecting any kind of pressure loss. So, we can write that P 2 and P 3 to be equal. So, let us replace P 3 with P 2, which gives P 2 to be equal to root over P 1 P 4. Now, if you divide both sides of this equation by P 1, then what we have? We have P 2 upon P 1 to be equal to root over of P 4 upon P 1, that is equal to root 8. So, actually we have derived this one as a part of the multi-stage compressioning exercise, but the same thing we have proved here, that is each stage is having the same number of or same magnitude of pressure ratio, and that can be directly calculated as a root of the overall pressure ratio. If you are talking about say kth stage of compression, then the pressure ratio for each stage should be equal to P final by P initial to the power 1 by k. So, now we have the numbers for us. Root 8, I have put the numbers to be equal to 2.83. This is for both the stages. Now, it is ideal intercooling. So, we have T 1 equal to T 3, T 2 equal to T 4. Similarly, we have ideal reheating, so that we can have T 7 equal to T 9 and T 6 equal to T 8. So, you have to calculate the temperatures. Now, there is no isentropic efficiency. So, it is quite straightforward. Then we have information given as T 1 and T 3 to be equal to 300 Kelvin and T 6 and T 8 to be equal to 1300 Kelvin. So, T 2 upon T 1 should be equal to P 2 upon P 1 to the power k minus 1 by k. From there we can get T 2 and T 4 to be equal to 403.83 Kelvin, the same number that we calculated in the previous lecture. And similarly, we can do the calculation for the reheating part or for the multiple stages of turbine. So, there we can write T 7 upon T 6 to be equal to P 7 upon P 6 to the power k minus 1 upon k. Now, though we have not done, but this being ideal scenario in case of that compressor also, sorry, in case of turbine also. So, there also the pressure ratio should be equal to root over 8 for each of the stages. So, from there we can calculate T 7 to be equal to T 9, which is equal to 965.74 Kelvin this case. So, how can you calculate the work outputs now? For the total work input requirement for the compressor, for each stage it should be equal to Cp into T2 minus T1 and should be equal for both stages. So, it is twice Cp into T2 minus T1, and that will be coming to be equal to 208.698 kilojoule per kg. Similarly, for turbine it will be twice into the work output from each stage, which should be equal to Cp into T6 minus T7, that is equal to 4671.863. Combining these two, we have net work output to be equal to the turbine work minus compression work to be equal to 463.165. So, we have got the work ratio or work output, and now the back work ratio RB should be equal to the compression work by the turbine work. So, putting the numbers, it is equal to 0.311. The back work ratio remains the same, work output also remains the same despite the presence of the regenerator. Now, we have to calculate the thermal efficiency, and there the role of the regenerator comes into picture, because had there been no regeneration, then the total temperature rise for the air inside the combustion chamber would be from T 6 to T 4, but because of the presence of regenerator, it is happening only from T 6 to T 5. So, first we have to identify point number 5, and as we are talking about an ideal regenerator as well. So, your T 5, that is also equal to T 7 and T 9. So, it is very straightforward now. The total amount of thermal energy requirement, then in case of the combustion chamber, it will be equal to Cp into T6 minus T5. If had there been no regeneration, this would have been T6 minus T4, but it is now T6 minus T5, and the energy required in the reheater, which is T8 minus T7. This of course remains unaffected because of the regeneration. So, total amount is coming as 671.86, and then the total thermal efficiency, that should be equal to W net by Q in. So, this number will be coming as 68.93%. This is the thermal efficiency. If you compare this one with the problem that we solved yesterday, where there was no regeneration, there the efficiency value that we got was something like 44.8%. So, you can clearly see there is such a significant improvement in the efficiency simply by introducing an ideal regenerator. So, regeneration is a very useful process, though there is no change in the net work output or work ratio or back work ratio, but there is significant change in the heat input requirement and hence the thermal efficiency of the cycle. Another interesting conclusion we can get it from there, if instead of having two, if we put multiple stages of compression and multiple stages of expansion, then under ideal scenario, that is with infinite number of expansion and compression, it should resemble the Ericsson cycle. Then what would have been the efficiency for the Ericsson cycle? The thermal efficiency for that Ericsson cycle should be equal to the thermal efficiency of the corresponding Carnot cycle working between the same two temperatures, because Ericsson cycle is also an totally reversible cycle. So, it should be equal to 1 minus the lowest temperature of the cycle by highest temperature, which is 1 minus lowest temperature in the cycle is 300 Kelvin, highest temperature is 1300 Kelvin. So, it is 1 minus 3 by 13, and approximately will be coming to be equal to 76.92%. So, while just introducing two stages of compression, we can see there is about 24% increase in the thermal efficiency, but just increasing the number of compressions and expansion stages to infinite, you are going to have, sorry, I tell the wrong thing. While introducing a simple regenerator with just two stages of compression and two stages of expansion, we are having an efficiency of 68.9%, a 24% increase compared to the no regeneration scenario. With increasing the number of expansion compression stages, we can have at most a further 8% gain, which may not be worthwhile in most of the practical scenario, considering the complexity requirement to have so many number of stages and also the space requirement for this. So, generally it is restricted only to 2 or 3 stages of compression and expansion. Now, we have a more complicated problem which is really very large, and read the problem statement very carefully. I am giving you the diagram first, so that you can directly compare with the diagram. Here we have a 5 megawatt gas turbine plant. It is operating with two compression stages. So, this is the LP compression stage and this is the HP compression stage, and perfect intercooling in between the stages. So, you are having perfect intercooling, that is once it is perfect intercooling. So, we can easily say that T3 is equal to T1, and also the pressure ratios are equal, that is P2 upon P1 should be equal to P4 upon P3. The overall pressure ratio is given as 9. So, here it is given as P4 upon P1 to be equal to 9. So, pressure ratio for each stage is equal to root over of 9, that is equal to 3. Now, look at the turbine side. Okay, what other information is given? The temperature of gas at the entry to the HP turbine is 650 degree Celsius and is reheated to 650 degree Celsius after expansion in the first turbine. So, we are having ideal reheating as well. So, in this case you have T6 and T8 to be equal to each other, which is 650 degree Celsius. The exhaust leaving the LP turbine passes through a regenerator with a thermal ratio of 0.75 or effectiveness of 0.75. I intentionally have used the term thermal ratio because though effectiveness is the common name, but in several places thermal ratio is the one that we can see. So, the regeneration is done. The air inlet temperature to the unit is 15 degree Celsius, which refers to this state number 1. isentropic efficiencies for compression stage is 0.8, turbine stage 0.85, and we have a mechanical efficiency of 98%, which is considered for both power shaft and the compressor turbine shaft. In this case, both the compressors are coupled with the HP turbine. So, the HP turbine is driving both the compressors, as mentioned here. The HP turbine is driving the compressors and the LP turbine is driving the generator. Now, the mechanical losses needs to be considered, and we have a mechanical efficiency of 98% for this particular shaft and also for this particular power shaft, which also you have to consider. We can neglect all the pressure losses and changes in kinetic and potential energies. As pressure losses are neglected, so we can easily say that pressure in the intercooler remains constant, that is P2 is equal to P3, and also pressure inside the combustion chamber remains constant, that is we have P4 to be equal to P5 to be equal to P6. Similarly, we have P7 to be equal to P8. And also, as the TS diagram is shown there, from the TS diagram we can also say that the pressure at the inlet, pressure of air at the inlet to the LP turbine stage or LP compression stage rather, should be equal to the pressure at the end point, that is we have P1 to be equal to P9 and P10, or I should have written here P1 to be equal to P9 equal to P10. So, here we are talking about at most 4 pressure stages. One pressure stage which corresponds to the air inlet pressure and the gas exit pressure passing through the regenerator. The second pressure stage is the LP turbine to LP compressor to the HP compressor stage. The third pressure stage from HP compressor to the HP turbine stage, and the fourth pressure stage from HP turbine to the LP turbine stage. The TS diagram is also shown accordingly. So, we have we can clearly see this is a pressure stage number 1, which corresponds to the inlet air and also the exhaust gas. Then this is the second pressure stage from LP compressor to the HP compressor, the third pressure stage from HP compressor to the HP turbines, and the fourth pressure stage from HP turbine to the LP turbine. So, this is the diagram. Now, you have to solve this one carefully. We know the pressure ratio for the compression side, but nothing is given about the turbine side, because here it is mentioned about perfect intercooling, but for regeneration nothing is given. Of course, temperature is mentioned that it is heated up to the same temperature, but that does not mean that perfect reheating, because no information is given about the pressure ratios. Now, as intercooling is perfect, so we can go step by step. For process 1 to 2, we can easily write T2S upon T1 to be equal to P2 upon P1 to the power k minus 1 by k. Okay, some additional informations which I have not noted here, those informations are given. So, for air we have Cp equal to 1.005 kilojoule per kg Kelvin and k equal to 1.4 for the compression side, that is for both LP and HP compressor. Okay. For gas on the turbine side, we have Cp equal to 1.15 kilojoule per kg Kelvin. This is Cp gas, this is Cp air, this K air, and K gas for this expansion process in both the stages of turbine is 1.333, and gas in heat exchanger, here the properties are similar to these values. So, gas is having the specificity of 1.15 and exponent of 1.333, whereas for air the Cp is 1.005 and K equal to 1.4. So, here as we are talking about air, so we should write it properly as T2S upon T1 to be equal to P2 upon P1 to the power Ka minus 1 by Ka, giving you some value of T2S to be equal to 394 Kelvin. And now the isentropic efficiency is given for the compressor. For isentropic efficiency, what should be the expression for this? it should be the ideal temperature rise, that is T2s minus T1 by actual temperature rise is T2 minus T1, which gives you T2, which will be slightly greater than T2s, and in this particular problem it is coming to be equal to 420.5 Kelvin. I am writing approximate numbers, you please do all these calculations on your own. So, the work input requirement in this first stage of compression WC to be equal to Cp air into T2 minus T1, and as we are talking about perfect intercooling in between multi-stage compression, the total compressor work should be just twice of this, and this work input requirement for the compression stage is then coming to be equal to 2 into 133.1 kilojoule per kg of air flow rate. Therefore, the work that the HP turbine needs to produce should be equal to this compression work divided by the efficiency of the corresponding shaft, which is, I am talking about this compressor turbine shaft, which is having a mechanical efficiency of 98%. So, this should be equal to 2 into 133.8 by 0.98. So, slight increase from 266, which is coming approximately 272 kilojoule per kg. So, this is the work output from the HP turbine that we are getting. 2% of that actually we are losing because of the frictional behavior of the corresponding shaft. Look at the process 6 to 7 which is happening in the HP turbine. So, there we can easily write WHP turbine should be equal to Cp gas into T6 minus T7. From there T6 is given because it is given to be 650 degree Celsius. So, if you put the values, then you will be getting T7 to be equal to 686.5 Kelvin. Now, isentropic efficiency for the turbine is also given, which is the actual temperature loss, which is T6 minus T7 by ideal possible temperature or maximum possible temperature loss T6 minus T7s. From there we can get T7s to be equal to 645 Kelvin. Now, the actual temperature at the end of HP compression process is 686 Kelvin, but had there been an isentropic compression, the temperature would have been 645 Kelvin. Now, what is the usefulness of this T2s? This T2s is the one which can be utilized to get the pressure at the end of HP expansion, because that information is not given to us. For the compression side, we know that both stages has equal pressure ratio. From here we can calculate the pressure P2 or P3, but that information is not given for the turbine, that we can get from here. So, we can write P6 upon P7, we can write T7s upon T6 to be equal to P7 upon P6 to the power k for the gas side minus 1 by k, to get the P7 upon P6, or I should say P6 upon P7, because P6 is the higher pressure, to be equal to 4.19. Exact value is not required, not given also. So, P6 upon P7 is 4.19, and we know that P6 upon P9 should be equal to the overall pressure ratio, which is P4 minus P4 upon P1 is equal to 9. So, we can write this to be equal to P6 upon P9 P6 upon P7 into P7 upon P9 to be equal to 9, and as there is no pressure losses, so P7 and P8 should be equal. So, dropping this, we have P8 upon P9 to be equal to 9 by 4.19, which is 2.147. So, the two stages of turbine are actually not having the same pressure ratio, their pressure ratios are different. In the first stage we are having 4.19 as the pressure ratio, whereas in the second stage it is almost half of the previous level, 2.15 only. So, use this pressure ratio now. to get the information about the temperature at the end of LP compression stage or LP expansion I should say. So, we can write T 8 upon T 9 S to be equal to P 8 upon P 9 to the power K gas minus 1 by K gas. From there we are getting T 9 S to be equal to 762.6 Kelvin, and again using the isentropic efficiency for this LP turbine stage to be, we have actual temperature change, that is T 8 minus T 9 by ideal temperature change, which is T 8 minus T 9 S, getting T 9 to be equal to 786.7. So, we have the temperature. So, the work from the LP turbine, I should write this as HP turbine, work from the LP turbine then is coming to be equal to Cp for the gas into T 8 minus T 9, and so W net should be equal to W from, this is W from LP turbine, I have mistakenly written as HP. So, work output that we are getting from the LP turbine plus work produced by the HP turbine minus the compression work. Now, these two are cancelling each other and this should be multiplied by the shaft process to the net work output, which is coming to be 153.7. So, we have to calculate the cycle efficiency. We have got the net work output from this cycle for this. So, we have to get the efficiency now. To get the efficiency, you have to make use of the information about the reheater. So, for the reheater, the effectiveness is defined as actual heat transfer. So, how much is the actual temperature rise for air, which is T 5 minus T 4, and maximum possible temperature rise, it could have been T 9 minus T 4. So, from there we can get T 5 to be equal to 695.2 Kelvin. So, Q in, then we are adding Cp for in the gas in the combustion chamber as Cp into T 6 minus T 5, and in the reheater Cp into T 8 minus T 7 to be coming to be 534 kilojoule per kg. So, the thermal efficiency for this cycle is the net work output that we have just calculated, and this Q in, for this particular case it will be coming something like 28.8%. So, this is the thermal efficiency for this particular cycle, and we have to calculate the work ratio as well. So, to calculate the work ratio, we have to calculate the net work output by the gross work output. Now, how much is the gross work output? The gross work output is the work produced by the HP turbine plus work produced by the LP turbine. So, if you do the calculation, it will be coming to be equal to 0.358. We could have also calculated the back work ratio from there, and the final answer that we have to calculate is the mass flow rate. Now, how to get the mass flow rate? This is the information that we have to make use of. 5 megawatt is the net output that we are getting from the gas turbine plant, and this is the net work output given in kilojoule per kg. That is for 1 kg per second of flow rate, we are getting 153.7 kilowatt of power output, and total output from this plant is 5 megawatt. So, just use that information, that is going to give you the mass flow rate to be equal to 5 megawatt, that is 5 into 10 cube kilowatt divided by this 153.7, which is coming to be equal to 32.6 kg per second. This is the way we can solve quite complicated problems with gas turbines also. It is a quite practicable problem. Of course, one thing we have neglected, that is we have assumed no pressure losses in the component, but we have considered intercooling, a perfect intercooling. We have considered an imperfect reheating, though that gas is reheated back to the initial temperature, but the pressure ratios are not equal, and we have also considered the regeneration to get the final results for this. This way, please try to solve some more problems from the textbook. Here I can't remember whether I have mentioned in my previous two lectures or not. While for the earlier weeks I have primarily followed the books of Sengel and Bowles, and in certain situations the book of Sontag. Here I am mostly following the third textbook that we have suggested for this course, the book of Applied Thermodynamics by Dept and McConkie. You can check the details that is provided in the concerned web page, where the entire bibliographical details of that particular book is available. You can purchase that book if required at all. May not be required, because if you are following the lecture, I think that should be sufficient, and you can also get lots of material on internet for this. Try to solve a few more problems to clarify or to get a hold on the process that we have followed here this. So, that takes us to the end of our week number 6, where we have focused on the gas turbine cycles. So, we started with the classification of heat engines, particularly the reciprocating and rotary type of heat engines. Then we introduced the ideal Brayton or Joule cycle, which is the ideal cycle for gas turbines. We discussed the role of isentropic efficiencies for both the turbine and compressor for the Brayton cycle. Then we discussed three different ways of improving the performance of the ideal Brayton cycle. First is multistage compression with intercooling, then multistage expansion with reheating, and third is recirculation or regeneration. Actually, I should not have written recirculation, and the better term is to write regeneration. Do not use the term recirculation, that is a typographical error. It is regeneration, it should be regeneration. And finally, we talked about the practical gas turbine cycles, where all these three kinds of methods are present. We can have intercooling with multiple compression stages, 2 or 3 stages of compression. We can have reheating with 2 or 3 stages of expansion, and definitely we can have regeneration. Only we have not solved any numerical problem which involves pressure losses in the components also, but that can also be there, which primarily affects the properties of the gas mixture and also the properties of air. You may get problems involving the pressure losses in your textbooks, particularly in the book of Dept and McConkie. So, that is it for week number 6. In the previous 3 weeks, or I should say from week 4, 5 and 6, we have talked about the power cycles involving gas as the working medium. We have talked about the air standard cycles for reciprocating engines, and here we have talked about the cycle for rotary engine or gas turbine. In the next week onwards, we are going to enter into the steam side, and we shall be talking about the steam power cycle. So, thank you till then.